Hello guys, welcome to another episode at IB Electronics World, and today we are going to discuss the ADC conversion part number 2. We are going to include in this tutorial interrupt service routine and also the hardware implementation. But let's try to understand in a simple way what is the interrupt service routine. It's a software process invoked by the interrupt request from the hardware device. It handles the request and it sends it to the CPU, interrupting the active process. When the ISR, the interrupt service routine, is complete, the process is resumed. I will give a very simple example, which is a hardware interrupt. In the electronics, it's just an alert which is sent from the external device, in our case the analog signal, let's say power supplies, and when we actually apply that voltage, we will have the hardware interrupt, which goes to the processor to read the voltage and then do something. So it's interrupting by something. Let's try to implement that in the code. Again, our favorite page here is the datasheet of this microcontroller. So you need to go in the section with the interrupt controller register 1. So if you are using a different microcontroller, you need to go in that section. And the first register bit is the NSTDIS, which is an interrupt nesting disable bit. In that case, we are not going to include that in our code, but we need to make sure that it's deactivated, and we don't want, because actually we don't want to mess up with that. So let's go back and then try to make it organized. So this is to register for interrupt. And it will be n underscore NTSTDIS equal to 0, because if we are going to activate that bit, what it means that the interrupt, it can go within another interrupt. It can cause a mess into your code. You need to be very, very sure that you know how you can handle that configuration. But in our case, we don't need to do that. We are just going to simple set up the interrupt configuration. Let's go back to the dataset. All the rest bits for math, arithmetic, DMA, we're not going to use that, so I'm going to continue. The next register is the interrupt flag status register 0. As I said in the previous episode, we are not going to set any DMA, but ADC1 conversion complete internal flag status bit, yes, we need this to be, it's very important flag. If this bit is set, the interrupt service routine is called, you need first of all to clear that flag. Otherwise, it can cause, again, you can mess up with your code. So it's very good to start with the clearing the flag. So that means set it equal to 0. And AD1F equal to 0. That means it's going to clear the flag, and then we are not caring about UART, we are not going to use any SPI. So interrupt enable control register, it's very important. So here we have a DMA again, we are not going to use that, but we are going to use the conversion of enabling. So we are going to say it's equal to 1 because we want the interrupt request to be enabled. So we want to enable the interrupt. So we go back to our code and say underscore AD1IE equal to 1. We go back again. Next important register is the interrupt priority control register, which in the IPC register, in our case number 3, and is the ID1 IP. Here it says the highest priority is the number 7. As I explained in the previous tutorial, 111 is equal to number 7, and it's number 7 the highest priority, and the lowest is priority number 1. And if you select the number 0, it's disabled. So in our case, we can use either number 3 or 2. I don't think that it's really matters, to be honest. So we're going to use number 2. And then AD1IP equal to 2. Yeah, pretty much that was all. Another very important thing is you need to add the attribute. It depends on what compiler you're using. Because I'm using XC16C, you need to add the attribute for the ADC interrupt. In particular, these attributes are platform specific extension which is used by the Microsoft for this specific compiler. So you can copy that from what compiler you are using here. And then, so if you are going to copy paste it from this bit, you need to include what you are going to use then. Because you need to use this attribute for the interrupts, you need to use this attribute for the ADC interrupts. So in that case, if you are going to use for ADC interrupt, you need to include underscore ADC1 interrupt. But if you are going to use a timer, you are going to say T1 interrupt. And into this attribute, you need to again clear the flag. So we can copy, paste. The first thing that you need to do is just clear the flag again. And then you need to create a new variable, which is going to be global variable, so it will be outside of the main function, and we are going to call ADC value, and it will be just an integer. And it will be equal to 0, just in case we want to initialize it as a 0. And we need to say, actually, you need to copy paste it. It's easier. Copy paste it and equal to an ADC1 buff 0. And this is exactly the buffer we are going to store this variable into this specific buffer 0. And then it's for your reference, because I had some warnings in the compiler, so you need to use the prototypes of the functions, and just in that case you're using void and the name of the function, and then void in the brackets and semicolon, and you will be fine. You are going to remove the warnings. And here we need to create a float number and float type variable, which is going to be the name analog value is equal to 00, and then in the while loop, this float type variable is equal to the ADC value multiplied by 3.3 volts divided by 496. Don't forget to add some brackets because otherwise we'll not understand the priority. And then we will say if this number here is greater than number 3. So actually what we are going to do, this number here, it's going to be equal to the ADC value from the buffer, the number we are going to receive from this buffer. It's going to multiply it by 3.3 and then divide it by the resolution, and it's going to give us the number, the actual voltage. I had initialized previously the lat B, so here the RB5, it will be an output for the blue LED, and then number 7 it will be green LED, and number 8 red LED. So in the first case, if it will be greater than 3, all the LEDs are going to be on, and the second case it will be if it's greater than the 2, the green and the red LED will be on. If it's greater than number 1, the red LED will be on, the rest will be off, and in any other combination all the LEDs are going to be off. So let's try and test it. It's successfully built, but let's see the design, what we have actually implemented in the hardware. So you can see that the RB, we are using a resistor 330 ohms and LED, and we are using again 2 resistors and again 2 LEDs which are connected to the ground, and we have also powered everything on the PIC microcontroller, and we are using a potentiometer which is connected to the ground and to the plus 3.3, and it's also connected to the analog input pin RA0. But let's see on the hardware here. So at the moment we have 0.02 volt, and once we are going to increase the voltage, you will see the first LED is going to light on. The second LED, it will start light on, the green one. You see that it's greater than 1 point something, and it goes to 2, and it's fully, and then the third LED start turning on, and once we reach the point of 3 volts and greater than 3 volts, we can see that the 3 LEDs are on. And this was the tutorial for today. Thank you for watching. If you like this video, please thumbs up, and please subscribe and share this video. Thank you.